Thanks again for joining us for our weekly Urban Water Innovation Systems webinar series. We're excited to continue our Thrust A seminar series with a follow-up to last week's Modeling the Metropolis project. And today we're going to have a presentation by Dr. Matt Georgescu from Arizona State University.
Thank you, Sarah. It's fantastic to join everybody. Thanks very much for the opportunity. I think it's a very nice segue from Ellie's discussion last week, which focused very much on the nitty-gritty details of the way urban models work and urban parameterizations work, and their incorporation into broader meteorological and climatological models. The focus here today will be essentially to extend the utility for some of those models to address future environmental change in urban areas. And before I begin, I would like to stress that really leading this effort is Scott Kranhoff. He's been doing the heavy lifting. Mohammed Mustawi, grateful to him for his excellent participation as well. And it's really been a whole group of folks that I'm going to acknowledge at the end of this discussion. So let's begin with a little bit of motivation. So we know that we live in an increasingly urban world. If you focus on the upper left-hand panel and you look at the intersection between the yellow line and the red line, you see that roughly in 2007, 2008, urban population equaled that of rural population. That is when the magical 50% threshold of global inhabitants resided in urban areas. And if you follow that red line all the way out to the end of the right-hand side, you'll notice that urban population projections by the middle of the coming century indicate essentially a doubling relative to rural populations. On the bottom left-hand side, what we notice is the relative urban population for specific subglobal geographic regions. So, for example, Asia, Africa, the green contour, all the way down. And so we noticed that through the early 2000s, extending to about 2030 or so, peaking at about 2030, the relative urban population for Asia peaks, it dominates the global urban population, but begins to descend thereafter as Africa's urbanization process begins to ramp up in earnest. And so what this means essentially is extensive conversion of natural lands to engineered landscapes, and of course to sustain livelihoods as well, to agricultural landscapes as well. Significant landscape conversion is projected through 2030 and beyond. How much exactly? Well, according to Karen Sato in a paper published in 2011, roughly the surface area of Mongolia is projected. That is an extensive amount of urban infrastructure. And so immediate questions come up, immediate questions arise as to what sort of infrastructure there exists to sustain livelihoods of the many millions of people that are going to be residing in these areas. And the globe has taken notice. Of course, the scientific community is paying increasingly large notice. The Urban Climate Change Research Network's second assessment report on climate change in cities, I'll refer to it as ARC 3.2. Their aim is to provide information that city leaders, we're talking about government, private sector, NGOs, non-governmental organizations, and the community at large, is to assess current and future risks within cities, including enhancing resilience to climate change and climate extremes. And the publication of this second assessment report is due out in September 2017 by Cambridge University Press. ARC 3.2 presents really a very broad synthesis of the latest scientific research on more than 100 cities across the world, integrating, so part one, for example, if you follow my cursor, across several cross-cutting themes that focus on integration of mitigation and adaptation rather than having them as separate elements. Urban planning and design, which was the focus of my contribution, equity, environmental justice, and economics, finance, and the private sector. Part two focuses on urban ecosystems, three on urban infrastructure, and finally on governance and urban futures. So in essence, ARC 3.2 fully endorses the United Nations New Sustainable Development Goal, which is to make cities and human settlements inclusive, safe, resilient, and sustainable. The urban planning and urban design chapter that I contributed to, chapter 5, promotes forward-looking avenues of cooperation between communities, the private sector, public-private partnerships, and the organizations that make up our cities to promote resilient urban areas by highlighting not just biogeochemical impacts, essentially the reduction of emissions of greenhouse gases, but by promoting solutions that are oriented under a biogeophysical framework, essentially how we build our urban environments. In order to understand that, we have to understand the impacts that our urban environments are having on the regional climate and how to promote socioeconomically oriented solutions. And this is, of course, not new. The high-impact journals, such as Science, hosted by AAAS, had a special issue last spring, last May, I believe. Special issue was entitled Urban Planet, and the image that you see in front of you stems from one article entitled Cities Are the Future. So rapid urbanization is overtaxing the planet, but it may not have to if we undertake some of these solutions oriented around urban infrastructure, energy systems, water systems, governance, and socioeconomic elements as well. The year before that, Nature had a very similar but correspondingly or relatively smaller feature entitled How Cities Can Beat the Heat. And the author of that piece, Hannah Hoag, talked to a number of climate scientists in different areas of the United States, and I believe different areas of the globe, if memory serves me right, to try to understand what are different municipalities doing in different areas to try to promote the incorporation of different strategies. For example, the deployment of cool roofs, which we'll talk about more extensively in forthcoming slides. So Los Angeles, for example, that's the image that you see before you. Los Angeles in 2014 ruled that new and renovated homes must have cool roofs. How they define cool roofs and what the level of cooling was that was required became kind of a gray or black box. Nevertheless, research continued into the different aspects, different technologies, different solutions that can be promoted. More recently, this is actually as of, I believe, last week or maybe the week before, Hauer, published in Nature Climate Change, published a very interesting study that looked at end-of-century impacts on sea level rise across the United States and the implications for migration of these communities to inland areas where they are not adversely affected. And what they found was that metropolitan areas in Texas, inland areas in Florida, the Atlanta metropolitan area, and the Phoenix metropolitan area, including Mesa and Scottsdale, with no adaptation are going to undergo considerable increase in population resulting just from this displacement of U.S. Citizens as a result of sea level change. And with some level of adaptation, these numbers are, of course, reduced correspondingly. But again, this raises very important questions about whether the urban infrastructure is prepared to withstand the range of pressures ranging from heat to sea level rise and the implications for migration. So how do we address these overarching concerns? Well, we do it through modeling. And Ellie gave a very nice talk more focused on urban perspectives last week. I'm going to begin very generally here and introduce modeling very generically, in a very idealized manner. Essentially, modeling consists of just a couple of things, what it really boils down to. And so we're going to begin this discussion by looking at an idealized temperature distribution across an imaginary metallic plate. Okay. Now, it's important to characterize this metallic plate as having finite boundaries. Okay. So the plate, of course, does not extend toward an infinite space. And this will come back. It's an important element that's going to come back, and I'll remind you of this later on. So the first rule, whenever we're modeling anything, is to establish what our model is. The model is just a set of principles, a set of rules that you, the modeler, establishes. So for this particular instance, we simply state that the temperature at any point will be the average of all the temperatures of surrounding points. Okay? So our model simply consists of the summation of all the grid cells surrounding a particular grid cell and then dividing by the total number of grid cells that are surrounding it. That is our model. We can choose that model to be, once again, whatever it is that we want it to be, but we wanted to keep things relatively simple here. The second part is the establishment of initial and boundary conditions. Okay, so our thermal plate must have some characterization of initial conditions. What is the initial temperature distribution of the plate? Okay. Similarly, since our plate does not extend in space infinitely, we must establish some boundary conditions. Okay, so we're going to set the initial temperatures at interior cells at 50 degrees. We're going to constrain the boundaries of the plate at 20 degrees Celsius initially and throughout the simulation. And just to make things a little bit more interesting, we're going to assume that we have a direct heating source in the upper left-hand corner of this plate, where we will maintain a temperature of 100 degrees Celsius. And then we let the model essentially iterate as many times until it reaches equilibrium. And what you noticed on the right-hand side is that towards the end of this very nice toy simulation, the temperature really doesn't undergo much further change. So the principal take-home messages from this illustration are the following. Our model is simply a set of rules that we established. In this particular case, the set of rules that we established was a simple averaging of all the adjacent grid points to calculate a new temperature. And the second was the realization that we need both initial but also boundary conditions for utility across areas where we don't have information. So we take that information and then we dive deeply into climate modeling. And with climate modeling, the set of rules is considerably more complex, of course, where we have to account for issues like incoming solar radiation, atmospheric scattering, but also scattering from cloud particles, cloud growth, and various forms of precipitation. What is the depth of the clouds? What is the type of precipitation and the intensity? And of course, what happens near the surface. And so we have to characterize the land surface itself, topography, type of trees, its phenological characterization, and the exchange of energy and matter within the land atmosphere continuum. If we're focusing on urban areas, the situation is a little bit different. Well, essentially, it's not that different, but what we have to characterize is a slightly modified version of energy exchange at the surface because of the incorporation of varied land cover and surface characteristics. And what this actually means is that within urban areas, shortwave radiation is absorbed differently, simply because less of the sky is apparent from near the surface, and therefore different rates of shortwave radiation are absorbed within the urban canopy relative to the outlying areas. Similarly, long-wave radiation is emitted differently, and so it might be absorbed by certain facets of the building environment, but a reduced amount is emitted out to space, which of course restricts the nighttime cooling capabilities, and this is what is widely known as the urban heat island effect. So land cover and surface characteristics contribute a significant portion of the way urban areas modulate their regional climate relative to outlying undeveloped areas. But in addition to that, we also have to consider the level of human activity. And the level of human activity can consist of anything from human metabolism. Essentially, one can think of humans as batteries. We emit heat, and in very dense environments, human metabolism can become an important part of the overall energy budget of the urban area. But primarily dominating the level of human activity spectrum are anthropogenic heat from the way that we essentially use energy. So we think about traffic patterns, of course, and cars, and incomplete combustion, and therefore release of energy. The way we use energy for air conditioning, especially in semi-arid, very hot environments such as the southwestern United States. And also the aerosols and chemistry that modulate the capability of shortwave radiation to reach the surface because they change the optical characteristics of the urban environment. So one of the important characterizations of urban environments is this morphological change. Essentially, if we're in, let's say, Central Park and we look up, if we lie down in the middle of the street, and of course we don't recommend that, but if we do that and we look straight up, what we notice is that a very small part of the sky becomes visible. Okay? So what this means is that unless the sun is directly overhead, there will be a modification in regards to incoming solar radiation because it doesn't strike at nadir. And similarly, during also daytime, but also more importantly during nighttime hours, long-wave radiation emission cannot escape directly out to space, but is primarily absorbed within the different facets of the urban environment. What complicates things is that urban areas are all different. And so you see here really a tremendous variability, complexity of different types of cityscapes from different cities across the world, and resulting in different view factors, which means that they all represent different ways in which incoming solar radiation is received at the surface, outgoing long-wave radiation is emitted back to space, or in many cases not emitted back to space, which has implications for near-surface temperature, mixing of the low-level environment, and if you include other characteristics such as traffic patterns, emissions of pollutants, things can get very complicated. So in reality, urban areas are completely different. How different? Well, traffic patterns are different. How folks drive can play a very important role. What type of a car is it? Is it a fuel-efficient car or is it not a fuel-efficient car? Is our cityscape vertically very vertical, or is it not, as is more common over European cities? Is the urban area very widespread and taking over a huge amount of expanse, as is the case over Phoenix, Arizona, or does it include more green space? So according to the United Nations, the situation is actually quite complicated. There is no strict definition of what urban means. And if you include the variety of administrative definitions that incorporate the word urban, there is an excess of 70 different definitions of what urban constitutes. And so this becomes difficult from a modeling perspective, because how can we model what we don't actually know? And so we have to make some assumptions of how we define urban in models. And the urban modeling community has really made a lot of progress from utilizing what are referred to as bulk parameterizations a couple of decades ago, more recently up until the late 90s and early 2000s, essentially just modifying the biophysical characteristics of a particular area to represent what it corresponds to within an urban area. Significant progress has been made until the urban climate modeling community now has integrated either a single layer or a multi-layer model with different land use and land cover classifications incorporating urban classes. For example, the National Land Cover 3-class urban database allows an urban climate modeler to characterize urban areas according to 3 different densities of urban classification. Now, within our urban modules, within our urban parameterizations, it is important to realize that really the representation of the actual urban environment is in this canyon-like, or what I like to refer to as Lego block representation. It is not an ideal representation because it doesn't actually correspond to real on-the-ground representation. And so a lot of remote sensing work, LiDAR work is currently occurring right now to represent, for example, the sky view factor here. So the terms that we talked a few minutes ago, which represent essentially the amount of open sky that is available for modulation of incoming solar radiation or emission of outgoing long-wave radiation. In addition to this, there's a lot of tuning that goes on. In this particular case, this is the WRF model, but for all urban climate and meteorological models, and Ellie described very nicely some of these issues last week. So the rest of this talk is going to be focused on urban physical impacts and urban adaptation strategies. And so I'll just briefly mention 3 very common strategies that are going to be repeated throughout the remainder of this talk. On the upper left-hand side, we refer to as cool roofs and materials. I should say that all of the impacts of all of the targeted impacts of these strategies are to reduce temperatures. Cool roofs and cool materials reduce temperatures by reflecting a greater amount of incoming solar radiation. Therefore, less solar radiation that is absorbed results in reduced heating. The impact is similar for green roofs, but the mechanism is different, as the primary mechanism whereby cooling occurs is through the evapotranspiration of water, either direct water from the leafy structure of the material or through a soil substrate. In the southwestern United States, in particular in Phoenix, there has been an attempt to increase vegetation coverage, in particular to increase tree coverage within the more densely populated regions of the metropolitan Phoenix area to 25%. In this case, the principal cooling mechanism is not suggested to be evapotranspiration, but through provision of shading for walking pedestrians. Nevertheless, for these trees to subsist and remain healthy, a considerable amount of water will be necessary. So a first attempt at some simulations to try to understand local impacts associated with different urban expansion strategies we conducted here in our group back in 2013. And what we're looking at are summertime temperatures focused for the southwestern United States, extending into the central United States. And what we're looking at the top panel is a difference in maximum urban expansion minus a contemporary urban expansion. For the middle panel, we essentially place these cool roofs that I mentioned a few minutes ago on top of the maximum expansion, and we noticed what the simulation results are. And finally, we utilized a minimum urban expansion scenario. All of these expansion scenarios were obtained from the local Maricopa Association of Governments, and their focus is essentially to promote sustainable urbanization for not just the county of Maricopa, but for the broader metropolitan area. And so what we notice is that locally, temperatures due to a maximum urban expansion scenario are in excess of about 3 degrees Celsius. These hatched lines indicate statistical significance. The deployment of cool roofs reduces this warming down to, for the most part, less than 2 degrees, but in large areas, less than 1 degree Celsius. So the effect of cool roofs is very noticeable and very significant. And finally, a reduced urban expansion scenario essentially yields the same result that you see in panel B. So that's interesting, and it suggests very nice impacts, very important strategies that can be used to promote cooler cities, especially here in the Southwest. What we notice in the central part of the United States is additional warming, and in some cases, some of this is statistically significant, and it appears for all of the simulations. So previous work by Francina Dominguez had calculated through a different modeling strategy that essentially anywhere between 20 to 30% of the south central precipitation during the summertime is due to water vapor evaporating from the southwestern United States. So essentially by paving over these regions, these expansive regions over the state of Arizona, we are now modulating the hydrologic cycle and essentially instituting a teleconnection pathway that removes the capability of cloud formation over the central United States. Now, in reality, we can never actually perform this simulation because one would not expect Arizona, for example, to urbanize at the expense of the rest of the country. You would expect urbanization to occur simultaneously over different areas of the country, of course, at different rates. So the Environmental Protection Agency developed what is referred to as the Integrated Climate and Land Use Scenario. It's a data set that is very similar. It's in the same vein as the IPCC SRES scenarios. They conducted socioeconomic assessment to calculate urban which locations are expected to urbanize. And these are a number of different projections. And what I'm showing you here is the urban cover in 2010 on the left-hand side, and the A2-2100 projection of urbanization on the right-hand side. This was work published by Bierwagen and colleagues back in 2010. And you'll immediately notice the Central Valley of California, for example, becomes significantly urbanized. The Front Range of the Rockies, Arizona, considerable urbanization over the eastern portion of Texas, Florida, and the eastern seaboard. And so the question was, can we relate urban relative to greenhouse gas-induced climate change? And what I'm showing you here is a very simple calculation. Essentially, the numerator is urban-induced climate change, and we define climate change as effects on near surface temperature. And in the denominator, it's greenhouse gas-induced climate change, with the metric being the same, near surface temperature. And so we don't want to focus on any particular pixel in this particular case, because we don't know what's actually going to happen out to 2100. So all of these different panels for the different regions of the United States, what they indicate is that the effect of urban-induced temperature change is not negligible relative to greenhouse gas-induced climate change. For all of these different pathways of urbanization or climate change, there is some effect, let's say 20% or 30% for one particular scenario. If I focus over the mid-Atlantic United States, there is some effect that should not be disregarded due to urbanization and the physical processes and the modulation of incoming solar radiation and outgoing long-wave radiation that we discussed previously. Now, one shortcoming of this work, which we're aiming to address now, is that these simulations, the urban expansion simulations, were not simultaneously conducted with greenhouse gas-induced climate change simulations. Those data were obtained differently from a different data set that did not include urban impacts. And so the assumption was immediately that these effects are linearly additive. And so we delve into the research question, and I'll just read from the following because it's a very important question. Does greenhouse gas-induced climate change and urban development interact to alter urban temperature, or is the assumption that we made previously incorrect or correct? Are they linearly additive? In addition, how much of the projected warming can be offset by urban heat mitigation strategies? And finally, although it's a topic of our work, we're not going to talk about it at all here, but how do urban development and heat mitigation strategies impact precipitation? So for this work, we're utilizing the Weather Research and Forecasting model, the model discussed by Ellie last week. We're focusing on 10-year continental United States simulations and 20-kilometer resolution. So not the high-resolution, short time period simulations that were discussed last week, and that will be the focus of future work as well, but climate scale integrations. We're outputting information and relevant meteorological data every 3 hours, and the reason that we do this is that we aim to quantify impacts on the diurnal cycle, not just averaged over any particular summer, although we won't be showing for the context of this presentation, we will not be showing diurnal cycle results. On the right-hand side here, what you see is an assortment of physics schemes that were utilized as part of this work. I should mention that we did a number of simulations. One of my PhD, actually two of my PhD students, Meng Wang and Melissa Wagner. This is work just recently that came out in Journal of Climate. And so what each one of these different panels, A, B, C, D, and so forth, what each one of these panels indicates for the top temperature and for the bottom precipitation are different combinations of physics options. How do you know what physics options yield the best results? And so the panels that I'm showing you here are what are referred to as Hofmöller diagrams. And so on the x-axis, you see latitude bands, and on the y-axis, you see time. And essentially what you're looking for is a lack of these colors to represent maximum agreement with observations. And you'll notice that, for example, for panel A, which represents one set of physics combinations, you'll see some red and you'll see some blue, which is the oscillatory behavior of the seasons. But in general, there's quite a bit of red and quite a bit of blue. In other words, agreement is not as good as we would hope. If we move over to panel H, for this particular set of physics combinations, which is what is utilized here and what is stated here on the right-hand side of the slide, So for example, utilizing the GREL scheme for cumulus and a particular microphysics scheme and so on and so forth, this yields the best combination, the best correspondence to observations for temperature and similarly for precipitation. Okay, so now to get back to our central question. So what we're trying to answer is what are the separately climate change impacts due to urbanization, and separate for that, what are the greenhouse gas induced climate impacts, and then are these two forcing agents linearly additive or not? So in order to address this, and again, I remind you that these are 10-year regional climate model simulations across the United States. In order to address this first question, so the climate change effect, so greenhouse gas induced climate change, we conduct a simulation which we refer to as base case, okay? The climate scenario is contemporary period, 2000 and 2009, which means that we have to utilize certain contemporary reanalysis product to force our model at the lateral boundaries. If you recall our discussion at the very beginning, our model is finite. It does not extend across the entirety of the globe. And an urban development scenario corresponding to ICLUS 2000. And similarly, we repeat this experiment, the climate change experiment, with a climate scenario corresponding to the end of the century and the same urban development scenario. So the climate change effect is very simple. It's just if we use the same nomenclature that we see here on the first column under code, T of BC, so the effect of climate change minus the base case gives us the climate change effect. The urban effect, very similar. We conduct an additional simulation, which we refer to as BU, so it's base case plus urban, so urban development. Same climate scenario, and now we include ICLUS 2100 as a representation of a maximum urban projection. And so the effect of urban development, if we remain with temperature as the example, although any metric can be used here, is simply T of BU, the urban development, minus T of B. And finally, what we're aiming to calculate eventually is the interaction effect. Okay, so in order to calculate the interaction effect, we have to include an additional simulation, BCU, so climate change plus urban, so climate change plus urban development, where the climate scenario is now corresponding to the end of the century, and the urban scenario is simultaneously corresponding to the end of the century. And so once again, utilizing temperature as an example, T of BCU, the climate change plus urban development, is simply equal to the base case plus the effect of large-scale climate change plus the effect of urban development plus the effect of any interactions. And this is the term that we're after here, okay? Because we have numbers to quantify the remaining terms. So if we now replace the English with our code that we used here in the first column, and cancel any like terms, and rearrange, what we notice is that we're left with the effect of interactions, if we go all the way to the right-hand side here, that corresponds to the following. Temperature of BCU, so climate change plus urban development, minus temperature of BC, so just climate change, is simply the urban effect in a projected climate, the projected climate from the end of the century, minus the projected urban effect in a contemporary climate. Okay, so this is how we calculate the effect of interactions. Now, a couple of words about the incorporation of greenhouse gas-induced climate change for our simulations that drive our regional climate model. One of the models that we use is the NCAR Community Earth System model, and we utilize this model to provide initial conditions, boundary conditions, sea surface temperature fields, and spectral nudging fields as well. So the design of experiments includes 10-year periods at the beginning of the century, in the middle of the century, 2050 to 2059, and at the end of the century, 2090 to 2099. The driving meteorology, these are the lateral boundaries and the initial conditions that I mentioned at the very beginning, come from a number of different sources. For example, the NCEP final analysis is one type of possible source. The European ERA interim is a different source. Similarly, we repeat experiments with CCSM for different representative concentration pathways. 4.5 is essentially a reduction in greenhouse gas concentration, and RCP 8.5 is a business as usual approach. For the end of the century, we additionally conduct simulations with another model, the GFDL Princeton model, and we repeat these for RCP 4.5 and 8.5. For this talk, we're going to be looking at results focusing on just the NCEP final analysis driving meteorology. So this is the reanalysis product that we use, and the second being the ECMWF, the ERA interim. So these are different data sets that can be used to drive, to represent current meteorology. These are the different boundary conditions and the initial conditions that can be used. And we'll be focusing solely on the CCSM RCP 4.5 and RCP 8.5 as driving conditions for future projections to the end of the century. For the ICLUS, for the urban representation, of course, observations corresponding to 2000 and different types, essentially a maximum urbanization extent A2-2100, minimum urban extent corresponding to B1 scenario that is essentially reduced population, somewhere around 400 to 450 million people by the end of the century for the contiguous United States. And we conduct base case simulations, cool roof simulations, the way I explained them before, and green roof simulations. So let's look at some of the results. So again, I remind you that the one of the principal questions that we have is to try to quantify this interaction behavior. Are these different forcing agents simply linearly additive, or are they nonlinear? And so we begin by looking at urban development using contemporary climate. And so WRF in this particular case, using contemporary climate, is driven using FNL reanalysis data. Okay, and this is what the pattern looks like. So essentially, we see localized warming between 1 to about 3 degrees Celsius, corresponding to areas undergoing urbanization. Then we conduct the exact same experiment, but using a different future climate. So 2090-2099 corresponds to CCSM RCP 8.5 climate. And so what is the effect of urbanization on the right-hand side here? Well, it's pretty similar. Qualitatively, there are some small differences, but quantitatively, where you undergo urbanization, the model picks up this warming generally up to about 1 to 3 degrees Celsius. So I remind you now that the effect of the interaction is simply the impact of urban development under the future climate minus the impact of urban development under the contemporary climate. So what does that look like? Well, here's the interaction effect, and what you see is a broad warming, generally about 0.5 to 1 degree Celsius locally over the southern tier of the United States and the southeastern United States. And over the western United States, the interaction effect is actually negative in a few locations, including the Sonoran Desert and the Central Valley of California. So now we wanted to repeat this experiment, but a key difference is that the current climate is being represented by a different reanalysis data set. So the ECMWF ERA interim data set. So our lateral boundary conditions and our initial conditions for the current climate, we are now using a different reanalysis data set. And broadly, when we look at the impact of urban development, we notice that warming is generally about 1 to 3 degrees Celsius, so qualitatively very similar to what we saw before. We now repeat the exact same simulation, again, RCP 8.5 for the end of the century. So this looks like the previous map that we saw, although we have conducted this simulation with GFDL model as well, driving WRF, and the results are very similar. And now we simply take the difference between projected urban development minus urban development for the contemporary climate to result in our interaction effect. And what we notice now is that the interaction effect looks broadly looks considerably different than the interaction effect utilizing a different contemporary climate. So all the broad warming in the central and southeastern United States has dissipated. Essentially what we're looking at is a little bit of noise at this point. We have a similar question, try to understand what the climate effect is through utility of different representations of contemporary climate. So if we utilize contemporary climate utilizing FNL reanalysis data, and compare this to RCP 8.5 for 2090 to 2099, this is the CCSM model, what we notice is broad warming that is greater over the western United States and can exceed 7 and 8 degrees Celsius, averaged over the entire summertime for the 10-year period, and a lot less warming, reduced warming, or little warming over Appalachia and the southeastern United States. The same calculation using era interim as the driving meteorology for the contemporary simulation yields a different picture. So quantitatively, the maximum warming is reduced compared to what we saw with FNL, but the warming hole that was evident in along Appalachia and southeastern portions of the United States is now absent. So I remind you what the urban impacts due to the different driving meteorologies for FNL and era interim look like. And now what we want to calculate is what are the relative contributions of urban-induced warming for FNL separately from era interim. And if we focus on the left-hand side, we notice that urban-induced warming generally, so we're calculating this over urban areas explicitly, is about 1.5 degrees Celsius. Climate change-induced warming, however, is about 3.5 degrees Celsius. So clearly, climate change dominates, but the effect of urban areas should not be omitted, which is consistent with what we've seen previously. If we utilize era interim, the relative impact of urbanization-induced warming is a little bit smaller relative to climate change-induced warming over those same urban areas. If we focus on RCP 4.5 now to drive future 2090 to 2099, so it's the same model, but it's reduced concentration pathway, what we notice now is considerably less warming over the United States, and the warming hole has actually now resulted in some slight cooling over the eastern half of the United States. Similarly, for the era interim, representation for contemporary climate, we have considerably reduced warming, generally not exceeding 2 to 3 degrees Celsius, and once again, no evidence of a warming hole over the eastern United States. If we try to quantify impacts just over urban areas using FNL as the driving meteorology for contemporary climates, what we notice is that urban-induced warming in this case exceeds warming due to large-scale climate change. That is slightly reversed if we use the era interim to guide contemporary climate. So incorporation of green and cool roofs for the future leads to the following results. So now we've changed the shading a little bit. So we have a blue representing cooling, and essentially you would expect the cooling to occur over the areas where these cool and green roofs are deployed, which is consisting of essentially cities. So the maximum impact should coincide and does coincide with the urban infrastructure. Where are the cities located? One slight difference that you notice for cool roofs relative to green roofs, so qualitatively these look very similar, but quantitatively the impact of cool roofs is a little bit greater than the impact of green roofs. Again, these are averages, 10-year averages across summertime. Okay, so one of the questions that we posed earlier was, what is the capability of these adaptation strategies to offset urban-induced warming? So this is the urban-induced warming on the left-hand side, and this is the cool roof-induced cooling on the right-hand side. And so a difference between the two leads to essentially a lot of blue shading, which is a representation of complete offset of urban-induced warming and additional cooling. Okay, this additional cooling, of course, can counteract, can offset some portion of greenhouse gas-induced climate change, though, as we've seen, the relative contribution of urban-induced cooling depends both on the urban trajectory, the pathway of urbanization, and also how you represent current climate. That's very important as well. One additional element that we've incorporated into our work is, and this is particularly important from an urban planning perspective, energy demand perspective and provision, is to try to look not just at the changing extent of urbanization. So here we quantify the effect of urbanization during the nighttime hours. Again, it's a summertime average over a 10-year period. And we've seen this before, right? It's essentially warming between 1 to 3 degrees Celsius. But if we increase essentially the density of the built environment, so for the last 10 years, what the data actually shows us is that houses that are being built are bigger than they have been before. They simply occupy more space. If we continue this trend into the future, and it's difficult to predict if we will, but it's important to quantify the implications of this trend. If we continue to intensify or increase the density of our urban environments, well, one can clearly see much broader scale warming approaching 3 and even 4 degrees Celsius in some cases, but occupying large regional areas resulting from intensification. So just to conclude with some initial results from this work, the interaction and climate effects depend on contemporary driving meteorology. We see an interaction effect for FNL as the driver that is essentially about 20% of the urban effect in some regions, but also varies in sign. So over the western United States, we saw that the interaction can actually be negative. Okay. Urban expansion warming is consistent across RCPs, reanalysis region, generally between about 1 to 2 degrees Celsius, which is 30 to 40% of the maximum greenhouse gas concentration change pathway, and between 70 to 120% of a reduced greenhouse gas concentration pathway on average. Some of the ongoing work, what I've shown until now, and really what most of the work has focused on until now, is broad summertime averages. And of course, it's not the case that things are completely sunny and cloud-free all the time. Similarly, it's not the case that, or it may not be the case, that the impacts are similar during the daytime compared to the nighttime. So one of the next few things that we're going to be looking at is to conduct these calculations separately for daytime versus nighttime, for clear sky periods, or perhaps focusing only on heat waves to try to understand how some of these impacts are behaving during extreme circumstances, during extreme meteorological events. In addition, additional capabilities have been added, and this is in collaboration with Project A2-1. So Ellie talked about this last week, provided a much nicer description. But what Scott has done and what Ellie's group has done, along with Ziwa and others, was to incorporate urban trees into WRF. And simulations are now being initiated to try to calculate what the effect of shading is on near surface temperature, and future work also to incorporate evapotranspiration as an additional cooling effect. So this simply increases the portfolio of heat mitigation and adaptation strategies that we're able to assess both regionally at high resolution, which I haven't discussed yet, but it is within our plans to do, and the broad-scale, continental-scale climate assessment that I've shown you today. So lastly, a lot of work has gone into this, so many thanks to PhD students, Meng Wang and Melissa Wagner, a high school student, Vishesh Gupta, who is the motivation for a new internship program that we're initiating. Actually, starting, the kickoff is on June 1st. Trying to pair faculty members with talented and very excited to learn about science high school students, and of course faculty members David Handula and Ziwa Wang. So with that said, I think that should leave a bit of time for follow-up and question. And I thank you for your attention and look forward to any comments that you may have.
Wonderful. Thank you, Matt. That was great. We do have a couple questions that have popped up throughout the course of your presentation, and maybe we'll get a couple more trickle in. So Forrest is wondering if the warming you refer to is exclusively air temperature warming or any other factors there.
Yeah, so all of the warming that I've referred to so far is the standard near surface 2-meter air temperature warming. So it is not skin temperature. So what we're trying to do is to focus essentially on the height that is most important from a human thermal comfort perspective, and with the full understanding that the skin temperature is going to be considerably higher. We can obviously assess that, and we will be looking into that. So Scott, who has conducted all of these simulations, is outputting a wealth of data that can be used for considerable additional work, ranging from pricing of water to human biometeorology, and we've discussed we've had initial discussions with other groups that may benefit from utilizing this wealth of data in excess of 100 terabytes. So what I've shown, so the long answer is it's near surface temperature at 2 meters. The answer is we've got temperatures for individual building facets, skin temperature, or the surface. Above the planetary boundary layer, we're going to be actually looking to see what impacts there may be there as well. I haven't talked too much about precipitation, but large-scale deployment of some of these strategies do have an impact on precipitation because of changes in buoyancy and lifting that are associated with the modification of the radiation budget. So there's a wealth of data that goes here, but strictly the information that I provided so far in today's discussion was near surface air temperature at 2 meters.
Okay, and just to kind of build on that question a little bit more, do you have a plan or protocol in place yet for sharing that data to interested parties?
We don't yet have a plan in place to share that data. One of the complications is that it is extremely bulky, but we are working with the PI of our project, Mazdak, whose computer science expertise, both himself and his team over at Colorado State, will facilitate a much easier way of downloading both data and metadata that are relevant to this data. So what we envision for the future, we haven't outlined this completely, but what we envision for the future is to have all of the relevant data available in a point-and-click type of format hosted over at CSU, probably through cloud services, such that anybody, whether it be a policymaker or a researcher, both within the United States or outside, can have complete access.
Great. Yeah, that's a topic that we'll hopefully be addressing and exploring during the annual meeting at the end of July and beginning of August. Okay, so moving on, we have another question from Ellie. He's wondering, how is the water budget of green roofs modeled, and is there any irrigation incorporated into that?
Yes, well, thank you for that question, Ellie. So we are actually calculating how much water is being added, something I hadn't done in previous work, but we're doing it now. So we're getting a running count for how much water is added. The incorporation of green roofs here is what I would refer to as a bulk approach. We're essentially putting an infinity pool on top of each roof, which is a maximum possible scenario that could be imagined. Some roofs, for example, are not flat and may not be able to support an infinity type of pool and are slanted, for example. So what we try to do in all of our simulations is to bracket the maximum possible range of impact. So in this particular case, there is no soil substrate that we're including, and what we're adding is 1 millimeter of water at the top of each roof to mimic what would happen if water availability was not a constraint. Obviously, water availability is a constraint, but by taking this approach, we can answer the following question: what is the maximum possible impact associated with green roofs? Anything less than this, if we had done anything less than this, we couldn't answer that question. So the next step is, of course, to integrate using a better representation, a more realistic representation of green roofs, such as you and Ziwa have developed, and couple this with WRF, and this has already been done actually for a couple of regions, Phoenix metropolitan area, and I believe it was Houston, and redo all of these simulations at higher resolution for future climate for the relevant UWIN nodes.
Great, thank you. I'm going to steal the screen controls back from you real quick here. but you're
No
still
problem.
on air. I just wanted to briefly introduce next week's topic. All right. And I'll keep monitoring in case any more questions pop up, but just wanted to remind everyone that next week we're going to have a presentation from Dr. Forrest Meggers. He's going to discuss approaches to innovative building systems and urban infrastructure. As always, I will be sure to send out a link to Matt's video. It'll be posted on our YouTube channel in the coming days. We got one more question here from Forrest. He is asking, how specific is the radiation simulation to spectrum ranges?
So I'm not sure if I understand that. So if this is a question in regards to how we characterize reflective capabilities of cool roofs, if that's the question, we don't distinguish between different parts of the spectra. It's a spectrally integrated characterization. But again, I'm not sure if I fully understood what the question was. In regards to characterizing the impact of different types of radiation schemes, we actually conducted several simulations. It was part of some of the model observational evaluation to try to see which radiation schemes perform better. And this is always difficult because one radiation scheme might perform better than the other, but in totality, the different combinations of convection schemes and boundary layer schemes and radiation schemes may yield better results. And this is one of the problems with all of these moving parts and such complex models. I'm not sure if my discussion directly answers your question or not, Forrest.
Here, let me try to unmute him. Let's see if this works. Oh, he's self-muted. All right. I think I might have. Oh, hey, Forrest.
I think I unmuted myself.
All right.
I was just saying, well, if we could follow up next week. I'm also in the car with my kids, so they may jump in. The question is more about exactly what Matt alluded to, whether the surface radiation budgets, when you model them for shortwave reflection of a cool roof versus sort of long wave re-emission from green roofs, whether that's accounted for, because there's re-emission in the infrared, obviously, by plant surfaces and by building surfaces, but when you do white roofs, you're reflecting a lot of shortwave, and that sort of changes the dynamics of what's going on at the urban surface. And then also water emits in the infrared, but doesn't emit sort of in the shortwave. It's translucent. So there's all these different effects that depend on the spectrum that you're modeling. I was just curious how many differentiations that are made in that domain, although at the large scale it's much harder to differentiate than at the sort of building scale. But we can discuss next week also. Yeah.
Okay. Yeah.
All right. Well, I'm gonna mute Forrest real quick. I haven't seen any more questions pop up, so I think we're going to go ahead and wrap up. Like I said, I'll send out the link once it's available on YouTube. And thank you so much for your time, everyone. Special thanks to Matt for that great presentation. And we look forward to seeing you all next week. Have a great day, everybody.